Hi everyone, I'm Sandy Lucas, the Program Manager for the Climate Variability and Predictability Program at NOAA. Thank you for joining us again for this webinar series called Years of Maritime Continent and Piston Field Campaigns. This is a continuation of a series of webinars for the CVP program, which started several years ago. Today's webinars are being recorded and will be available from the CPO website under the Climate Variability and Predictability section. You can see that link there on your screen. If you've missed any of our prior talks in the past CVP webinars, I encourage you to view them from our website. All sessions are now posted there, and they are easy to download on YouTube. So the Years of Maritime Continent is an ongoing set of international field campaigns and modeling efforts focused on the Maritime Continent region. YMC is led by the countries of Japan, Indonesia, and the US in partnership with several others. Of particular interest to NOAA and the Climate Variability and Predictability Program is to improve understanding of processes that affect the propagation of interseasonal oscillations, such as MJO, in the Maritime Continent and its broader region. MJO is important to local weather and climate, as well as having global teleconnections. However, the Maritime Continent region can sometimes act as a barrier to the propagation of MJO, and weather and climate models have a hard time reproducing this effect. In response to that need, the CVP program solicited for observation and modeling projects that investigate different processes that affect the MJO. Additionally, in collaboration with the Office of Naval Research, CVP supported several activities of the Piston Field Campaign. This year's webinar series covers the 16 projects funded by CVP. I really look forward to hearing the results of their research in this webinar series. I'd like to thank Dr. Victoria Breeze, our communication specialist, for her continued support during the second half of the series. Victoria will be describing the series and introducing our speakers today. So Victoria, whenever you're ready.
All right, thank you, Sandy. Hello, everybody, and welcome to the 7th of 10 webinar sessions on the topic of Years of Maritime Continent, which will feature 2 presentations per session and will run from September 10, 2020 to March 25th, 2021. This series of presentations will share the latest results from these projects and will allow the PIs to discuss the importance of their work, outcomes, and lessons learned with the broader scientific community. We hope you will enjoy today's talks and ask plenty of questions. As you listen to the presentations, if you have a question you would like to ask the presenter, please raise your hand. Raise your hand is a feature which you can find on the control panel for GoToWebinar. At the end of the presentation, I will unmute those who have raised their hands so that they can ask their questions using audio. If you have audio problems, I will ask you to please type your question into the questions box, which can also be found on your control panel. So, our first speaker today is Dr. Janet Sprinthal, a research physical oceanographer at Scripps Institution of Oceanography. Janet enjoys working with colleagues and students investigating the role of the ocean in the variability of the coupled air-sea climate system, with a particular focus on the Western Pacific marginal seas and the Southern Ocean. She is a seagoing scientist collecting in situ observations from ships and moorings, and also contributes to the Global Ocean Observing System. Janet, thank you so much for joining us. At this time, we will turn the controls over to you.
Okay, terrific. Okay, thank you very much, Victoria and Sandy, for this opportunity. I'm going to talk today about observed air-sea interactions due to barrier layers from the recent Piston Field Campaign. And I'd like to thank my happy band of co-authors here. This is a paper that we've submitted to Journal of Climate as part of the special Piston and CampX experiment. And it's just going to be, it's in its second round of revisions, so we're hopeful this time that it'll be published, so look out for that one soon. So first off, I thought I'd spend some time and just let's think about what is a barrier layer. Well, for most of the world oceans, we see the temperature and salinity are both well mixed to the same depth, and that consequently their density is well mixed to that same depth, and that is the mixed layer depth. But in some regions of the ocean, we see a deeper isothermal layer compared to a shallower isohaline layer. But that isohaline layer has a has a halocline at the base of it, and that halocline is strong enough to result in a pictocline, so density is only well mixed to the same depth as the salinity. The region between this deeper isothermal layer and the shallower mixed layer is referred to as the barrier layer. So it's salt stratified barrier layer. Now, what is a barrier layer to? It's a barrier layer to heat transfer because it results in reduced entrainment cooling, right? So because any water that can be entrained from the barrier layer into the mixed layer itself has the same temperature as within the mixed layer. It also, this shallower mixed layer can trap heat and fresh water in the near surface layer, and then that acts to enhance its impact on sea surface temperature as well as air-sea interaction. So there are lots of different formation mechanisms for barrier layers, and how I've shown that is from this great schematic that's we all show from Megan Cronin and Mike McFadden. And different mechanisms for barrier layer formation include rainfall, which can result in these freshwater pools on the surface layer, as well as horizontal advection, current shear and salinity gradients, and tilting of sea surface salinity fronts. The barrier layers that I talk about are probably caused mainly through rainfall. The piston area is this piston area is a well-known area for barrier layer formation. And in fact, this is a climatological map of barrier layer thickness as determined from Argo profiles for October, from the October climatology. And so you can see the piston area is characterised by relatively thick barrier layers. So we've had a number of different presentations so far about the piston field campaign, but I have to let this seminar speak in a standalone. So I just say that PISTON stands for the Propagation of Intraseasonal Tropical Oscillations. And the Piston Fieldwork campaign, at least the part that I'm going to, it was co-sponsored by ONR and NOAA CVP, and my part was funded through the CVP program. So Piston, this cruise in October 2018 was on the Tommy Thompson. It consisted of 2 legs. The first leg was out of Taiwan, and then we focused in this Piston observational area and did multiple surveys along roughly about 134.7 degrees east, 135 degrees east for most of August and September, and did a bit of a reconnoitre over here with the Japanese research vessel so we could get some dual Doppler radar measurements together. And then we had a port call into Palau the 10th through the 14th of September before returning to the Piston fieldwork area of the intensive observational location where we did another occupations along 135 degrees east and also deployed 2 moorings before returning to Taiwan. So as you've heard, Piston was very much a multiple air-sea study with many different measurement platforms, and this slide from Jim Moom shows a multitude of the different platforms that measured different aspects of air-sea interaction as part of Piston. And we've heard about some of these measurements from other talkers as part of this seminar series. My component of Piston was to take 206, well, not me personally, but me and many people who were on the vessel, to take 267 underway CTD profiles of temperature and salinity over the upper 400 metres. So it's an underway measurement. And you can see this photo up here of Zane Martin and Socorro Rodriguez and myself hard at work deploying the UCTD. I'm going to focus primarily on, we did multiple surveys along the 135 degree east line, like I said, and so that's going to be the focus of my talk today, is to talk to you about those different transects along those, along 135 east. First off, let's start having a look at the large-scale conditions that existed during the Piston field campaign. And what I plotted here is the climatological September SST in the contours, so you can see the warm pool region over here. And then in the shading is the anomalous SST that we experienced in September of 2018 during the piston campaign. So this green dot here represents the location of the fieldwork. And you can see, even though the piston region itself was near normal during that, at least during September of 2018, to the east of us in the tropical Pacific, it was characterised by SST anomalies of over 0.5 degrees Celsius, over 1 degree Celsius, in fact, for much of the rest of the Pacific. And this is indicative of the 2017-18 El Nino period. In fact, let's look at the large-scale atmospheric conditions, and the paper that I talked about, the Sobel et al. Paper, that shows a number of different ways we can slice and dice and represent the large-scale atmospheric conditions, but I've chosen here to show the outgoing long-wave radiation anomalies. They are averaged over 5 to 20 degrees north, and it's a Hofmüller diagram. So we have time running up the y-axis over the 2018 period, piston period, fieldwork period, from August through mid-August through mid-October. And then we have longitude on the x-axis, and this 135 east represents the location where most of our surveys were taken. So that was where the ship was mainly located. So in fact, we had during the piston campaign, as is sometimes the way, we experienced very little boreal seasonal, boreal summer intraseasonal intraseasonal oscillations, or in fact hardly any MJO variability itself. We had this one active event shown here that occurred in our region in mid to late September. The piston field campaign period was mainly characterised by synoptic scale variability, and these included these, passage of these 2 to 3 day waves, the easterly waves, including equatorial Rossby waves and mixed Rossby gravity waves and tropical depressions, and that included 6 tropical cyclones. We were just like bombarded with tropical cyclones in the Northwest Pacific that year, of which 5 reached Category 5 intensity. In fact, if we look at the large-scale conditions in the Northwest Pacific for tropical cyclones, this is a histogram of all the August-October storms in the Northwest Pacific, and in grey you can see the tropical storms, the Category 1 and Category 2 tropical cyclones, and then in orange we build up to the Category 3 and Category 4 tropical cyclones, and then in red we had those Category 5 tropical cyclones, and the dotted lines here represent the means in each of those 3 categories. So we see that in 2018 we had 5, like I said, we had 5 Category 5 tropical cyclones, and we have to look all the way back to 1970, 97, 98 to find a similar number that over the 30-year record. So which was also an El Nino year. So it's a very active year for tropical cyclones. So we're going to start off and have a look at some of the surface conditions that existed during the piston field campaign. First off, we're looking here at another Hofmüller diagram, only now we have the sea surface temperature anomaly from remotely sensed measurements. And this is the piston field campaign is now, the time is on the x-axis, and you can see the piston field work phase here. And then from the equator up to 20 degrees north. So as I said, one of the typhoons that went through was actually Super Typhoon Mangkhut, and that super typhoon originated as a tropical depression out in the Central Pacific around the 7th of September. But then by the time it reached our piston field area on the 11th to 15th of September, it had sustained maximum 1-minute winds wind speeds of over 70 miles per hour, the very definition of a Category 5 storm. So it passed through our region along 135 East, which is shown here, around lunchtime on the 12th of September in 2018. It was a very fast-moving storm. It caused a lot of devastation and damage and deaths in Guam and the Philippines and Taiwan. And so luckily, I think it was actually fairly lucky, but we had planned anyway to have a Palau port call around that exact same period when the storm passed through, when the typhoon passed through. And you could see the period when it passed through 135 here, represented by these yellow crosses. So even though it was disruptive for many of us with many of our travel plans and holiday plans and Palau and everything, it was somewhat fortunate that we were in port during the passage of this typhoon. So let's get back to SST. So you can see this is the passage of the storm here in the yellow crosses, and to the right of the storm, where we know from previous work, because of vorticity effects, that the ocean gets affected more on the right-hand side of the path of the storm in the Northern Hemisphere. And so in that region, we see quite strong cooling of over a degree centigrade, anomalous temperatures of over a degree centigrade in the surface layer. Now, it's also interesting to look at the salinity. This is the sea surface salinity along 135 again, from the SMAP satellite sensor from the equator up to 20 north, and again over the piston fieldwork phase. And we see again these yellow dots indicate the location of Super Typhoon Mangkhut along 135 east. And we see very salty water existed, anomalously salty water existed south of the typhoon pathway, whereas during the passage of the typhoon itself, it was much fresher to the north, and then became saltier after the passage of the typhoon. So that's what we see in the surface manifestation from remotely sensed data. So now if we look at the subsurface measurements that we have from our cruise data, I'm going to show you two surveys. One was taken before the passage of Super Typhoon Mangkhut, and the second was taken after the passage of Super Typhoon Mangkhut. So let's start. So this is the subsurface measurements from the conditions before Mangkhut, and what we see along 135, 134.7 degrees east. And in this top panel, we have salinity with depth and latitude. In the middle panel, we have temperature, and in the bottom panel, we have zonal velocity. So this was a pre-Mangkhut passage survey taken on the 8th of September. All the locations of the UCTDs that went in to make up this transect can be shown in the red crosses at the top of the panel. So in the near surface layer, we find very fresh and warm water, and that's indicative of the North Pacific tropical surface water that's derived from local rainfall variability, and that overlies this band of much saltier North Pacific tropical water, which actually is salty because it originates in the evaporative regime of the centre of the North Pacific subtropical gyre and then subducts into our piston region. And then that overlies the relatively fresher North Pacific intermediate water that is formed in the subarctic of the North Pacific. I've also plotted on here in blue is mixed layer depth, and in pink is the isothermal layer depth. So you can see we have a much shallower mixed layer compared to the deeper isothermal layer, and that we know is the barrier layer. So we have barrier layers that between the isothermal layers and mixed layers. Barrier layers were present before the passage of the storm, are relatively 10 to 20 metres thick. In terms of zonal velocity, not much going on, but we have this weak westward flow, and that's indicative of the North Equatorial Current that characterises this region. Now, after the passage of Mangkhut, again, we have salinity in this upper layer, temperature in the middle panel, and zonal velocity below. And then the passage of the storm, as I said, was roughly around 14 north along 134.7 degrees east at lunchtime on 12th of September. And after the storm, this survey south of 14 north, so that's on the left-hand side of the storm, we see an upper layer that's saltier, slightly cooler, and consequently denser. The subthermocline characteristics are cooler and fresher. And then we see the mixed layer and the isothermal layer have both deepened. They've both deepened and eroded that barrier layer. And actually, we can have we can drill down and get a better view of that somewhat just by comparison of two UCTD profiles that were taken both at 13 north and 134.7 degrees east. And in blue is temperature, red salinity, and black is density. So, and before Mangkhut is the light line, and after Mangkhut, the typhoon is in the red line. So we see in temperature, it's isothermal down to about 50 metres depth, but our density is well mixed only down to about 25 metres because in response to that salinity stratification. So we have barrier layers before the storm, like I mentioned here at this place, of about 25 metres. Then after the passage of the storm, we see that the mixed layer has deepened. The mixed layer has deepened and is well mixed in salinity and temperature, and it's now extending down to about 75 metres, and there's no barrier layer there. But wait, there's more. So we actually had measurements north of the storm after the passage of the storm from this survey after the passage after the storm. But unfortunately, the way of many field campaigns, we did not survey north of 14 north before the storm passage, so we can't really do a direct comparison. But what we can do is have a look at the conditions north of the storm, and that's valuable in itself. So again, this is the storm centre in this orange line, and then north of the storm, we see much deeper isothermal layers to the north, and also shallower mixed layer depth, but that means that there are barrier layers north of 14 north. In the subthermocline, all the isotherms and the isohalines are much deeper in the water column. That means it's fresher and cooler. And then velocity gets really interesting. In the velocity, we see this really strong jet centred around the storm centre, right, where we see this western flow to the north of the storm and eastward flow to the south of the storm. And that's probably a sign of near inertial wave activity. The strong eastward flow observed here in the subthermocline, it potentially is a sign of the surface near inertial currents generated during the storm passage that have subsequently propagated downward as internal gravity waves. So my last slide is returning back to the surface layers. And this figure shows temperature at 5 metres, salinity at 5 metres, and barrier layer thickness. And again, thin lines are before the passage of the storm, and thick lines are after the passage of the storm. And this is with latitude from 11 to around 16.5 degrees north along 135 east. So on the left-hand side of the storm, we see, even though the temperature is cooler, the water is cooler and also saltier, there is no barrier layer, and this saltiness and the relative cooling is consistent with entrainment of this water from within the barrier layer during the storm passage, because recall that there's not really a huge difference in temperature here because that's the water in the barrier layer is the same temperature as the mixed layer itself, and plus it's salinity stratified, so it's saltier water. North of the storm path, north of 14 North, we see a much stronger oceanic response to the storm as expected. So it's now very cool and very salty, and also we have very thick barrier layers. So we can conjecture a bit about what it might have looked like before or after the storm, before the storm. So if there was no barrier layer before the storm, then this response in the surface layer could have been from entrainment or upwelling, because the influence of the storm the mixing could extend deeper in the water column and bring up that cooler and saltier water to the surface. But then the cooling can also occur from enhanced turbulent heat loss associated with the increased winds related to the storm. So did the barrier layer form after the storm then, potentially through surface fluxes, through precipitation? So recall that the sea surface salinity from the SMAP measurements, the remotely sensed measurements, showed that during the storm passage there was very fresh sea surface salinity probably in response to heavy rainfall. And did that mean that the barrier layer formed quickly after that in response to the heavy precipitation in that surface layer? So in conclusions, I've shown you ocean measurements as part of the piston field campaign that showed very rich vertical structure, in particular barrier layers that we had existing prior to the path of the tropical cyclone could potentially trap heat in that near surface layer and in fact may have fueled the passage of the storm. Barrier layers can also moderate the storm response to the tropical cyclone passage, as we saw through the entrainment of that cool, salty water out of the barrier layer after the storm passage. So tropical cyclones were found to modify SST, sea surface salinity, the vertical ocean stratification and the currents as they passed over the piston regions. And these interactions need to be observed and modelled correctly in order to accurately predict future SST, the distribution and magnitude of ocean heat content, as well as the tropical cyclones themselves and the climate patterns resulting from that, from their presence. And I'll stop there and take questions. Thank you.
Thank you so much, Janet. At this point in time, if anyone's got some questions they'd like to ask, we have time for a couple. Please just push the raise your hand button and I'll get you unmuted, or you can type them directly into the questions box. All right, I see a question from Robert Joyce. Robert, I'm unmuting you. You should be able to unmute yourself as well and then talk.
Okay, well, this is Ping Z. Bob Joyce passed me his links on the table. It appears there are two Bob's names. I have a question. You briefly compare look at the satellite retrieved salinity and the instrument observed salinity profile. I have one question. Have you compared since the satellite retrieval is looking at the salinity at really the skin level? Have you compared how much the difference is between the skin that the satellite is supposedly observing and between the very first layer that your instrument can observe? Because the reason I'm asking this is because at the CPC, with support from CPO, we have been developing a satellite in situ blended analysis of salinity. We have been always wondering about that, how much that difference is.
That's an excellent question. It's a really good question. And yes, we expect there to be differences, right? Because we know that, that there's going to be near surface trapping of that freshwater pool, and how deep does it extend. And obviously my UCTD measurements are the the nearest to the surface is that 5 meters that I showed, you know, in the next to final slide. So I have to be brutally honest with myself here, is that when I was putting this seminar together last week, I thought, oh, I should look at the SMAP data. And so, you know, I pulled up the SMAP data and lo and behold, it was there. And I thought, oh, that's lovely. And then I thought exactly what you said. I thought I should put that on this last slide, and I never got round to it. But I will now. I will. It's a very good suggestion. So I have not personally looked at that, but I think it is of interest. And in fact, I'm sure you're aware, but it was a focus of the SPURS campaign too in the Eastern Tropical Pacific to look at the vertical distribution of salinity in the upper meters of the ocean. It's a very interesting question. Thank you.
Yeah, well, I think it will be very interesting to look into this, especially from viewpoint of the interacting or how the freshwater flux, like precipitation, will change the salinity. Because, you know, if the precipitation is very light, very likely it will only change the the skin level of the seawater, so that the satellite can see that, but not necessarily the instruments. But if you have a continuous heavy rainfall, which will deeply penetrate into the seawater, then there might be good correspondence between what satellite see and what the ship observation sees. And it would be interesting to see kind of how those kind of intensity and duration of precipitation will play into these processes.
Absolutely, it's very good. And actually that would be interesting even, you know, this is just the first of probably many articles that we'll publish with this data set, and it's just our first look at the large scale conditions. But yes, I think that your question's something that we can answer, and we have good precipitation measurements too during piston 2 that we can take advantage of. So I think that you raised some interesting issues for further investigation. Thank you.
Oh, okay, thank you very much.
Thank you.
Wonderful. All right. I'm not seeing any other. Oh, wait, a digital hand just appeared. I think we have time for a short one from Kelvin Richards. I've unmuted you. If you can unmute yourself on your side.
Yes, Kelvin Richards. I wanted to make one comment. And you say that barrier layers trap heat at the surface. It's actually the salinity stratification that is trapping the heat, and not what is happening below the mixed layer. So I think we need to be a little bit careful with the use of barrier layers, and in particular the thickness of the barrier layer. But south of the equator, you did see this very deep, the mixed layer was deepened very much, eating through both the salinity and temperature stratification. Are you able at all to quantify what impact this relatively narrow, what you're calling a barrier layer, has on the evolution of the mixed layer temperature?
Yes, I haven't looked at that yet, Kelvin. It is Kelvin. But and also I stand corrected. I stand corrected about the salinity stratification, and I will endeavour to be more careful when I talk about that in future. But yes, you're right. And I have not looked at that yet, but that is something that we plan to look at in the future, about trying to do a budget, you know, some sort of a budget analysis to see what impact it could have potentially on, if the heat content is sufficient, to look at the effect on the evolution of temperature and salinity in the mixed layer.
Thank you.
Thank you.
All right. Again, Janet, thank you so much.
Thank you.
We are going to move on to our next presenter now. So up next is a presentation by Dr. Naoko Sakaida, an assistant professor in the School of Meteorology at the University of Oklahoma. Naoko received her PhD in atmospheric sciences from the University of at Albany State University of New York and a Bachelor of Science at the University of Washington in Seattle. Prior to joining the School of Meteorology as faculty, she was a National Research Council postdoc associate at NOAA Esriel in Boulder, Colorado. Her research interests include understanding the dynamics of tropical clouds and precipitation in various scales and their interactions with higher latitudes. Naoko, thank you so much for joining us. At this time, we will turn the controls over to you.
Okay, thank you. So thank you for this opportunity to share my work today. What I want to share today is part of this CVP-funded project that looked at the modulation of the diurnal cycle by the MJO and the convectively coupled equatorial waves over the maritime continent. And this work's been done in collaboration with George Caladas and Juliana Diaz at NOAA Physical Sciences Laboratory. Okay, let's see if I can advance. There you go. Okay, so this work was motivated by many of the prior studies that have emphasized the important role of the diurnal cycle to the propagation of the MJO across this region. So this is one study from Lin et al. 2019 showing or demonstrating the importance of the diurnal cycle as the precursor of MJO propagation across this region. So on their figure, the left figure from their paper, this is showing the composite of the diurnal amplitude based on the location of MJO convection that is shown on the horizontal axis. And they further divided this to the MJO events that crossed over the maritime continent, and then the events that decayed or did not propagate through the maritime continent, which are shown in this two solid and dashed red line. So this diurnal amplitude, they're looking at the diurnal amplitude of the rainfall over the island region within the black box shown on the right figure. So what they're showing here is that when the MJO enhanced convective envelope is around 80 to 90 degrees, so which is when the MJO convection is still over the Indian Ocean, they're finding this significant amplification of the strength of the diurnal cycle of rainfall over the islands of the maritime continent. And that seems to be appearing more significantly when the prior to the MJO events that crossed the maritime, that were able to cross the maritime continent, therefore suggesting the diurnal cycle as the precursor to the MJO propagation. So this made me wonder, this made us wonder about whether how unique this feature is to the MJO, meaning we know that there are other large-scale disturbances such as the convectively coupled equatorial waves that can also disturb the diurnal cycle over this region, and we wonder if similar patterns can be seen with the other waves, which will be important for us to understand how this observed behavior is appearing, or what mechanism is controlling this behavior. So the simple question that I would like to address through this talk today is, how might the other equatorial waves modulate the diurnal cycle of rainfall differently over the maritime continent, differently from the MJO over the maritime continent? And the schematic on the left is showing the kind of idealized evolution of clouds and the environment through different types of wave. And the thermodynamic variability, like moisture, is considered to be generally similar across all waves. So if we expect the moisture to be the most important source to modulating the diurnal cycle, then we would expect similar response pattern in the diurnal cycle as all waves propagate across the maritime continent. So the second question that I would like to ask is, could such a modulation of the diurnal cycle be explained by the large-scale circulation and thermodynamic structure of the waves? So to answer these questions, the main data that we're using is TRIM 3B42 and GPM precipitation radar data. I'm mainly going to show the results with the 3B42 rainfall rate data, and this rainfall data is combined with ERA interim reanalysis data to look at the environment, the large-scale disturbance perturbations, and we'll be focusing, our study period is focusing on November through March in 1998 through 2016. So to do this, we first have to quantify the amplitude and the phase of the diurnal cycle. And we're doing this through harmonic analysis. So on the right here, it's some hypothetical evolution, 24-hour evolution of the rainfall rate. Diurnal amplitude represents the magnitude of the rainfall rate that varies within the 24-hour. And then the diurnal phase represents the local time at which the rainfall maximizes. We also need to identify the convective coupled equatorial waves and the MJO, and we do this using following Wheeler and Kelada's 1999 method, and we applied their method to filter the TRIM 3V42 rain rate for the selected wave number frequency band for each wave. And so the bottom right figure is showing the wave number frequency power spectrum of equatorial antisymmetric and symmetric signal of the brightness temperature from Kelada's et al. 2009 paper. And so there are different kind of waves that can be identified. For this talk, I can't talk about all of them, so I'll be focusing on the comparison between the three waves: the Madden-Julian oscillation, Kelvin wave, and equatorial Rossby wave. So the Madden-Julian oscillation is the interseasonal planetary scale disturbances. Kelvin wave is more of has a shorter time period, but also propagates eastward, whereas equatorial Rossby wave propagates westward on a time scale about 20 to 60 days. And we wanted to come up with a simple way that allows us to compare the sensitivity of the diurnal cycle to different type of waves. So we chose to use what we call wave phase diagram that is defined by two time series. So on the left figure, let's see if my cursor appears. I guess not. Oh, there it is. Okay. So on the top figure, the horizontal axis is the rain rate anomaly that is filtered for a particular wave of our interest, and then the vertical axis is time tendency. So this is these are rain rate at any selected location. So the difference of this index to more commonly used global EOF-based indices like RMM and OMI is that we are identifying the phase of the wave locally at some specific location. So in this diagram, we can define angle, and we define plus or minus 180 degrees as the center of suppressed convection, indicated by the minimum rainfall rate or negative rainfall rate anomaly. So on the right, I'm kind of showing the illustration of how this works. So this will be same for either the wave is propagating eastward or westward. So at that location, if you're in 100 plus or minus 180 degrees, you are under the suppressed convective envelope of any waves that is been identified. So the minus 90 degrees indicates the phase where the wave is convective. The active phase of the wave is approaching, indicated by the positive rainfall rate tendency. And then the 0 degree indicates the center of enhanced convection, indicated by the positive rainfall rate anomaly. So at that phase, you are under the enhanced envelope of convection. And then the positive 90 degrees around there indicates decaying phase of a wave, where at that location, the wave is moving away, either going east or west, and that's indicated by the negative rain rate tendency. So using this wave angle, we can composite anything. And for example, here is an example of a composite of diurnal amplitude as a function of the wave phase angle. So once we have this, we can then further diagnose how much the diurnal amplitude is varying along the life cycle of a wave, which will be indicated with this delta, the red delta. And then we can also identify the wave phase at which the diurnal amplitude is maximizing. We can apply this diagnostic technique to each grid point on the map, and we will come up with maps like this. So the top is showing the amount of change in diurnal amplitude along the passages of MJO at each location. So you can see that the diurnal amplitude is varying more over the ocean along the passages of the MJO, and while its magnitude of variability is quite small over the islands, as other studies and our prior studies have also indicated. Then the bottom figure is showing the wave phase at which the diurnal amplitude peaks with respect to the MJO. So the negative wave phase angle means that the diurnal amplitude at that location tends to maximize during the amplifying phase of the MJO, whereas the red or positive wave phase angle indicates the diurnal amplitude is peaking during the decaying phase of the MJO. So this map is very convenient at showing the geographical sensitivity or variability to of the diurnal cycle to a passage of any wave in one glance. So, so using this, we can easily compare the sensitivity of the diurnal cycle to varying waves. So here I'm showing the amount of change in diurnal amplitude with respect to the MJO on the top, middle is the equatorial Rossby wave, and then the bottom is the Kelvin wave. So you can see that the Kelvin wave by far has the stronger impact on the amplitude of the diurnal cycle. More interesting thing appears when we compare the wave phase at which the diurnal amplitude peaks with respect to the MJO and the Kelvin wave. So one thing you can see is that there are color changes across the topography in each island, so that the diurnal cycle responds differently over the east and west side of the topography. And this asymmetric relationship across the topography also reverses between the MJO and equatorial Rossby wave. So for the MJO, if you look at the western side of these mountains or islands, the diurnal cycle strengthens ahead of the MJO. So if this is a hypothetical time series of the rainfall rate with the diurnal amplitude peaking around time 0, then at that location, you tend to see the diurnal amplitude peaks followed by the passage of MJO convection. Whereas if you compare this to the equatorial Rossby wave, the opposite is happening. At that location, you're going to likely see the passage of the equatorial convection followed by that maximum amplification of the diurnal cycle. And if you go to the other side of the topography, the opposite is happening. The diurnal cycle strengthens behind the MJO, but ahead of the equatorial wave. So, but if we compare this to the Kelvin wave, something really different appears. So the Kelvin wave does not induce this asymmetric response in the diurnal cycle across the train. What you can see here is over most of the islands, you see this blue shading, which means that at all islands, either the east or west side of the island you are at, you will likely see diurnal amplitude peaking, which is then followed by the passage of Kelvin wave convection. So the first result here is that the MJO and the convectively coupled equatorial waves modulate the diurnal amplitude of rainfall quite differently. So now the question is how and why. So prior studies always give us some hint to understand this. So the schematic on the left is showing the different diurnal propagation behavior during the easterly and the westerly regime of the interseasonal lower tropospheric wind variability. So what they found is that during the easterly regime, the rainfall tends to preferably propagate eastward, and during the westerly regime, the rainfall tends to propagate eastward. So this lower tropospheric wind and its vertical shear, they may affect the diurnal propagation of rainfall through advection of clouds and generation of new convection as suggested by prior study. So this kind of makes sense when we think about the circulation structure of the MJO. So this is as illustrated here, and the MJO is propagating eastward. So if you're standing at one location, you're going to experience the easterly regime first, which would enhance diurnal cycle on the western side of the island, followed by MJO convection, and then you're going to see westerly wind approaching, which would then enhance the opposite, the diurnal cycle on the opposite side of the island, so which will be on the eastern side of the island. Then if this is the primary mechanism affecting the diurnal cycle, then we should be able to explain all this through the circulation patterns, because we know how the circulation tends to evolve with all these different kinds of waves. So these are showing the theoretical structure of Kelvin wave and equatorial Rossby wave. So with Kelvin wave, the structure is quite similar to the MJO. You would have easterly wind and then the convection followed by the westerly wind if you're standing at one location experiencing a Kelvin wave passing by. Whereas for the equatorial Rossby wave, which moves westward, so if you're standing at one location, then you would feel the westerly wind of the equatorial Rossby wave, followed by its convective envelope, followed by its easterly wind. So the difference in the circulation structure between the MJO and Kelvin wave might likely explain the different sensitivity of the diurnal cycle that we saw to these two waves across the topography of the maritime continent islands. So the question now we're going to ask here is that do the MJO and convectively coupled equatorial waves modulate the diurnal amplitude by basically modulating the propagation direction of the rainfall rate? So to answer this question, we now have to identify or diagnose the diurnal propagation of rainfall rate. So we're going to do this using at each 2 degree by 2 degree box centered on each grid point. So for example, in this box shown in red, we can look at the meridional or latitude and longitude time evolution of rainfall rate over the 24-hour cycle, and this will allow us to estimate the meridional and zonal propagation speed of the diurnal cycle of the rainfall. And we can simply shift the window and then find the continuous time series of the estimated diurnal propagation speed of the rainfall at each grid point. So once we have that, we can kind of look at the climatology, which is shown here. I know this is a very busy figure. I'll zoom in a bit. So let me do that. So here, now I zoomed in on the left showing the Sumatra, in the middle showing the Borneo and Sulawesi, and then the right showing the New Guinea. So the vectors is showing the climatological diurnal propagation direction and speed, and the shading is also showing the speed. So this technique generally captures this outward or the offshore diurnal propagation of rainfall, as you can see with the vectors pointing out from the island into the offshore direction. So this does capture this general kind of climatological characteristic, but of course there are always caveats to some methods, which I think I'm not going to talk about too much, but in general this seems to do a good, okay job. But what we really want to do is to understand how this diurnal rainfall propagation is varying along the passage of a particular wave. So to do this, we are first finding this the propagation speed of the diurnal rainfall at particular wave phase of a wave. And then we're projecting that speed or the vector onto the climatological propagation vector, which would give us a scalar quantity V. And its anomaly would tell us whether this climatological offshore propagation of the rainfall is being enhanced or suppressed at particular phase of a wave. So here's an example for during the amplifying phase of the MJO. So the vector is showing the propagation direction and speed of the rainfall rate at that location during this phase of the MJO. And then the red is showing the anomalous scalar V. So in the red region, which indicates enhancement of this offshore propagation of the diurnal cycle of rainfall, then you can see this vector kind of pointing in the same direction as the climatological rainfall, climatological propagation speed. Whereas in the blue region, where you don't really see large vector, or the vector points in a different direction than the climatological vector, which indicates suppression of this offshore migration of the diurnal rainfall propagation. So, so we can then use this to compare how the diurnal rainfall is propagating at different phase of waves, and we can compare those between the MJO and equatorial waves. They're both amplifying phase. So this is what it looks like here. On the left is showing the MJO, and on the right is showing the equatorial Rossby wave. So during this period, for the MJO, the enhanced offshore propagation of the diurnal cycle is occurring more on the western side of the island, whereas for the equatorial Rossby wave, that seems to be occurring more on the eastern side of the islands, which is consistent with our prior analysis. So in comparison to this, we can also look at the large scale structure of the wind that are imposed by the MJO and equatorial Rossby wave. So during this phase, the MJO here is showing the 850 hectopascal horizontal wind speed and direction anomalies. And here you can see that during the amplifying phase of the MJO, you are seeing easterly wind, which is as we expect based on the structure of the MJO. So during the amplifying phase of the MJO, it is imposing easterly wind anomaly that seems to be enhancing the westward propagation of the diurnal rainfall. In comparison with the equatorial Rossby wave, you can see that the circulation structure is a little more complicated. But for example, over the eastern side of New Guinea, you see that the equatorial Rossby wave is imposing westerly wind anomaly that seems to be enhancing the eastward propagation of the diurnal rainfall rate. And similarly, another quantity that prior studies have suggested to be important is the vertical shear of in the lower layer. And that is generally has a consistent direction as the lower tropospheric wind. So we can replace the easterly wind with easterly shear or westerly wind with westerly shear, and we see kind of similar results. However, the difference appear when we look at the Kelvin wave. So remember, the Kelvin wave was a little different from the MJO and equatorial Rossby wave in that that there's no asymmetry in the response of the diurnal cycle to a Kelvin wave. So in the amplifying phase of the Kelvin wave, this is showing the diurnal propagation strands. You can see it's kind of all red, and the vectors are pointing out from the island, meaning that the offshore migration of rainfall is enhanced on both sides of the island. Now, if we look at the wind or the vertical shear of the horizontal wind associated with the Kelvin wave, it is having the easterly shear, or as we expect during this phase of the Kelvin wave, we expect to have easterly wind anomaly. So with the Kelvin wave, there is easterly wind or easterly shear imposed to this region, but it is somehow enhancing the diurnal propagation of rainfall on both sides of the island. So there's no clear relationship between diurnal propagation of rainfall and the large-scale shear. And the variation of the diurnal cycle and diurnal propagation by the MJO and the convectively coupled equatorial wave does not seem to be explained just by lower tropospheric wind or shear direction. So then what else might be important? The other studies have suggested that the role of humidity as well. So the top left is showing the wave phase at which the column humidity peaks with respect to the MJO, and then the right is showing the phase at which the diurnal amplitude peaks. So if the column humidity peaks in sync with the diurnal amplitude, then these two patterns on the maps should have a very similar geographical variability, and which is somewhat true. But if we plot them against each other, so the black line is the one-to-one relationship. So you can see that there's some linear relationship between the timing of peak column humidity and diurnal amplitude with respect to the MJO, suggesting that the moisture perturbation is also important to the diurnal cycle. And if we repeat the same analysis for the MJO, equatorial Rossby wave, and Kelvin wave, this linear signal becomes more stronger for the Kelvin wave. But in general, for all waves, its modulation of column humidity is also tightly associated with the modulation of the diurnal cycle. So suggesting that the humidity might also play an important role in modulating the diurnal cycle. So in summary, we saw that the strong diurnal amplitude is often associated with enhanced or faster offshore propagation of diurnal rainfall over the maritime continent islands. And this modulation of the diurnal cycle depends on the type of the wave that it's passing through. And for the MJO and equatorial Rossby wave, the modulation seems to be mainly affected by the direction of the lower tropospheric wind or its shear. However, for the Kelvin wave, that does not seem to explain the variation of the diurnal cycle. For the Kelvin wave, the moisture perturbation seems to be the primary role, determining just enhancing the rainfall on the diurnal cycle over the entire island. And there are also some relationship between the column humidity and also the direction of the lower tropospheric wind of the MJO and equatorial Rainfall wave. The column humidity seems to play a more important role for faster propagating waves, such as the Kelvin wave. But there are also still some questions remaining, such as what are the relative roles of this lower tropospheric wind versus humidity in determining the response of the diurnal cycle to these waves. So thank you for your attention.
Great, thank you so much, Naoko. Everyone, if you've got a question you'd like to ask, please click the raise your hand button or type it directly into the chat. All right, I see Courtney has her hand raised. Courtney, you're unmuted on my side. You may have to unmute yourself as well.
I just did that. Okay. Hey, Naoko.
Hi.
So did you just look at November? You just looked through at boreal winter, right?
Yes, kind of extended winter.
Yeah. So do you think the season, what if you look at the other season, you know, boreal summer, do you think you'd get different relationships because of the large scale wind change?
Yeah, that's a great question. We haven't looked at that. I mean, it's not, I almost think it's hard to do like apple to apple comparison between different seasons because everything changes from the climatological state to even where these waves are occurring and also even their strength. So, but it'll be interesting to look at.
Okay, cool. And then I have another question. What if you had like really high resolution radar data? Would that add, you know, at high, you know, temporal resolution, would that change, you know, would that add anything to what you've looked at, or are you pretty happy with the, you know, the temporal and scales that you have?
No, actually, I am trying to look at more of the data set that Jamstack has shared over the website to look at more of the radar data now. So the high resolution data would probably give us more idea of how exactly these convection are evolving or propagating around these islands. So I think those will be interesting to look at. And of course, the radar data that you've been working with are.
Yeah, we should talk more.
Yes.
Sounds good. Oh, down.
All right, looks like there might be another either Robert or Ping Ping question.
Yeah, this is Ping Ping again, Ping Ping from CPC. Okay, you look at the diurnal cycle of precipitation, but precipitation usually is a much complicated phenomena. It's influenced by large scale things that you are looking at, but local effects are also important, like topographic effects. Have you and also the measurements of precipitation is much challenging, because especially in areas like Maritime continental, where you have a lot of mountains, those kind of things. Have you looked at the diurnal cycle of convection as indicated by satellite observed cloud top temperature? And by doing that, I think this also partially answers the suggestions Crony had. If you are looking at the cloud top temperature, that satellite data have much higher spatial and temporal resolution that will allow you to do more careful studies. And also, I think convection is less influenced by local effects kind of things. So maybe it will be interesting to look at that to see, you know, how different, how similar the diurnal cycle of convection is compared to the rainfall.
Yes, I definitely agree, and thank you for that suggestion. Yeah, with the topography, some studies have noted greater error in the estimation of the satellite-based rain rate. So, yeah, more data would definitely be interesting to add more understanding to this study.
All right, I don't see any other hands in the chat, and we're a few past 5, so Naoko, we're going to say with that, I would like to thank everyone for joining us for this set of presentations in our series on years of maritime continent. We would especially like to thank today's presenters for taking the time to share their work with us. The recording of today's webinar will be available within the next week on our website, cpo.noaa.gov/cvp. Our next webinar will be on February 25th, 2021. We hope to see you then. Thank you so much.